Hi, I'm Craig the geologist, and in the Keweenaw of Michigan, there is a stretch of shoreline where the rocks are beautiful. They go from fairly normal colored to a very dark red. And I don't mean just like a little bit red, faintly red, hey, there's a red hue there. I mean deep red, blood red. The shore turns to rhyolite. But what is rhyolite? How did it get there? And what can that rhyolite tell us about a period in Earth's history when parts of the Great Lakes were 1,000 feet deep beneath an ocean of roiling lava? Let's learn a little bit about our awesome rhyolites together. Come join me. I'm at Hunter's Point near Copper Harbor, and it's a beautiful little secluded shoreline here. Usually not very many people. I've got a bag full of pasties. I've got my family with me, and I've got a beach made entirely out of red rhyolite. Careful with those pasties, kid. All right. Would you just look at those beautiful red rhyolites, dappled with a bit of gray basalt mixed in. Now the rhyolite shores of the Keweenaw are not continuous. That's best illustrated from the sky. Here, from a drone's eye view of Hunter's Point, you can see that most of the shoreline out here in one direction is rock, just straight into the water. I don't mean like pebbles you can collect, I mean it's just consolidated rock. And then it goes to rhyolite right here. But then there are breaks in that where it goes back to rock and then rhyolite, and it's almost like the beach is being subdivided into small stretches of private beach that you can have almost to yourself. I'm out here on a very sunny, warm, beautiful day in August, and you can see it's not crowded. You can pick a stretch here and pretty much have it to yourself. It's really idyllic out there. The unique elongated shape of Hunter's Point is due to the way the rocks outcrop. And you can probably see that through the water here. The rocks rise up from beneath the water and encounter the surface. And it creates a series of ridges that go along the Keweenaw. And there's a whole geology lesson to that is best saved for another day. But the short version is that the heavy rocks in the center of Lake Superior have sunk, and that's pulled the rocks on the margins, like in areas like this, up and exposed them. The rocks of these rhyolite shores are mostly derived from the Copper Harbor conglomerate formation, which we'll talk about more in a few minutes. The rhyolite shores of the Keweenaw run along the northwestern stretch of the Keweenaw from about north and west of Eagle Harbor through Copper Harbor into no man's land, the wildlands of the tip of the Keweenaw. Hunter's Point here is probably the most accessible of the rhyolite shores of the Keweenaw. It is a private preserve, but it's open to the public. They ask that you do not collect there. Now, are you legally prohibited from collecting there? It's a complex answer. It's yes in some places and no in others. And is it ethical to collect there? That's a whole other question. We'll actually dive into that a little bit in part 2 of this series. Hunter's Point kind of encloses Copper Harbor. It is very easy to find if you have an eagle eye and you're watching the road as you drive south of Copper Harbor for the very small sign that will direct you to the location. But if you can follow the signs or follow your GPS, you can find it quite easily. While I get set up with my delicious lunch of pasties, why don't I take a moment and actually tell you what these rhyolites are. Rhyolites are lava rocks. They were erupted from volcanoes. Extrusive igneous rocks, for those of you who like your science with a little bit more jargon. No! No, 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 not that way, not that way, not that way, no! Well, I had this fantastic plan to have the camera set up and give a talk to you with a beautiful backdrop, but then the weather decided to give us 50-mile-an-hour wind gusts and knock the camera over a few times, which I can't afford for that to be happening. So Here we are. Let's just chat a little bit about these rhyolites. Depending on where my last clip got cut off, you may or may not already know that rhyolites are an extrusive igneous rock. They were erupted from volcanoes. Extrusive igneous rocks are classified based on color. Well, that's not actually true, but it is basically true. We can act as if it's true because while they're actually classified based on silica content, you can't actually see the crystals in most extrusive igneous rocks. They're very fine grained. And so you have to approximate the composition by color. And so you have a range of compositions in extrusive igneous rocks. Basalts, which are very dark, running up through andesites, dacites, and then rhyolites, which are very light colored. Now, that color is due to the amount of quartz in it, and also some lighter feldspars. So basalts have a lot of very dark mafic minerals in them, things like hornblende and amphiboles, pyroxenes, while things like rhyolite have a lot of quartz and feldspars, alkali feldspars, plagioclase feldspars, that make it very light colored, sometimes give it a slightly pink hue. The rhyolites of the Keweenaw Peninsula, though, aren't just slightly pink. They're a very deep dark red. And there is a reason for that, and that's a very high iron content in those. Most rhyolites don't have a whole lot of iron in them, but those Keweenaw rhyolites do. And when that iron oxidizes, it turns rust red, and that's what gives you that red color. The composition of those magmas control the style of eruption. As the silica content increases in a magma, the silica forms chains. They link together and they restrict flow. They increase the viscosity. Viscosity is a measure of how easily a fluid flows. So for example, water has very low viscosity. It flows very easily, very readily. Materials with a very high viscosity would be molasses, honey, tar, things like that. Well, as the quartz content increases, the temperature decreases in the magma and the lava thickens. It becomes more viscous. And so rhyolites get erupted in one of two ways, basically. Either they're squeezed out like very thick toothpaste from a tube, or if they've got a lot of gas content in them, those gas bubbles reach the surface where there's absolutely no pressure holding them anymore, and they pop. And when you get a few hundred quadrillion bubbles going pop at the same time, you get a massive explosion. Kablooey, you get something like Mount Pinatubo. Now, we don't actually know a whole lot about how rhyolites erupt because there have only been 4 documented rhyolite eruptions on Earth since the start of the 1900s. Despite the lack of observations, though, we do have a good general understanding of what goes on in rhyolite eruptions based on what we observe in the historical record and the little bit we've actually seen with our own eyes. Those rhyolites tend to form in one of two ways. First, a lot of eruptions will begin with rhyolite or some other very high silica magma being erupted at the surface. And that's due to the fact that the magma has had to melt its way up through the crust. So people picture a volcano, a crack ripping open through the earth and lava shooting out. And while that does happen sometimes, generally speaking, especially in the larger scale, lavas have to melt their way up from the mantle. And they're melting their way up through crust that is very rich in quartz and feldspar, those lighter minerals. The Earth's crust is enriched in those minerals because the Earth's crust is floating basically on the mantle. All the lighter stuff rises to the surface, all the heavier stuff tends to sink down towards the Earth's interior. And so that magma melts its way up, and as it melts its way up, it gets enriched in feldspars and quartz, and it cools down. It becomes a rhyolite. It erupts explosively or oozes out, and then you have the main eruptive phase, which is usually the more original composition magma coming up. And you'll end up with, depending on where you are, in Iceland, basalts, in the Andes, andesite, things like that. The other way you get rhyolites forming is through evolution of the magma chamber. Now, in a well-developed magma chamber at a volcano that's been erupting a lot, you have all the stuff that's easy to flow out of the surface, flowing out of the surface. But in the meantime, you have a lot of crystals left behind. You have some of the thicker material left behind, and it's crystallizing and congealing below the surface while the eruption is happening at the Earth's surface. And a comparison I would make is to a bottle of honey that's been left on the counter too long. You start to get those crystals forming in the bottom. And I think this is a really good analogy because this is literally what's happening in a magma chamber. You have your liquid flowing stuff at the top. You can still pour your honey out maybe, but at the bottom of your honey jar, those crystals are beginning to lock together and starting to make it really viscous, make it really difficult to flow. It's hard to get that honey out. Eventually, it might completely solidify and you have a granite, basically. You have intrusive igneous rock. Holy cow, that was a lot of wind. I really hope this is going to record well. Well, that happens in the magma chamber. But at the end of the eruptive phase, there might still be a lot of gas locked in that magma, and it's still going to want to come out. And so it will come up as a plug and kind of solidify in the vent. It might come out as a lava flow and go a very short distance. Rhyolites don't tend to travel very far. Because they are so viscous, they don't want to flow. Or if there's a lot of gas in there, it's going to come up and it's going to go kaboom, and you're going to have a massive, super violent eruption. That's what happened at future Michigan and the Great Lakes Mid-Continent Rift. You had an enormous flood basalt, one of the largest volcanic eruptions in all of Earth's history, take place. And that was the majority of which basalt, very liquid lava, stuff like you find in Iceland and Hawaii. But at the end of that eruptive phase, you have a lot of very highly evolved magma still trapped in the chamber. And at the final phase of the eruption, there were very, very large amounts of rhyolite erupted. Huge mountains of rhyolite in place, presumably through lava flows, although we do see evidence of pyroclastic flows, very explosive eruptions also. There are a handful of textures we see in rhyolite lavas. We do see vesicular lavas, although the rhyolites of the Keweenaw are too old for those vesicles to be intact. They're generally all filled with minerals, and they become called amygdules at that point. So we do see a lot of amygdaloidal rhyolites. We also see porphyritic rhyolites, that is crystals that were dragged up with that thick lava from the magma chamber. Like I said, there's a lot of crystallizing going on inside the magma chamber, and when those very thick, viscous lavas come up, they carry a lot of those crystals up with them. And so you get a lot of those porphyry minerals called phenocrysts locked in the lava, and we see those in the rhyolites as well. And finally, there's a really cool texture we see in rhyolites. It's one of my favorites, called flow banding. As these thick rhyolites flow, and they can be thick in both in terms of viscosity and in terms of their actual vertical thickness, as they're flowing, the stuff on the bottom, the stuff touching the ground, really isn't flowing at all. It's, sticking to the ground, and the stuff above it is flowing just a little bit faster, and the stuff above that's flowing just a little bit faster and faster, and you get countless shear zones where the rhyolite is basically sliding past each other very thickly. And where it's sliding past in those shear zones, you get flow banding. You get bands of color revealing the flow direction of the lava itself. It's very cool stuff. I'm looking forward to showing you some of that. Well, now that wintertime me is done fighting with the wind to explain this, and Hunter's Point me is sitting down for a nice family lunch, let's pop on over to Horseshoe Harbor and talk a little bit more about these rhyolites and the Copper Harbor conglomerate. I'm at a fantastic spot called Horseshoe Harbor here. You'll never guess why it's named that. It is this beautiful horseshoe-shaped harbor that just comes out like so, and does that on the other side, as you might suspect. The rocks here are beautiful red rhyolite all over. Not great collecting because it's all red rhyolite, and there are signs up asking you not to collect here. We'll address that in a minute. Now, these reefs of rock that partially enclose Horseshoe Harbor are made of Copper Harbor conglomerate. Let's have a close look. So as you can see, the rocks here aren't actually rhyolite. They're a conglomerate that's made almost entirely of rhyolite. Let's climb up and have a better look. All right. Oh, maybe I'm going to be documenting the way I fall down this thing. Let's see. Let's see how my climbing skills are in wet water shoes. One-handed, of course. Well, there we go. Success. So the rhyolites out here were erupted just over 1 billion years ago. The rhyolites were erupted at the tail end of the Mid-Continent Rift. Mid-Continent Rift was an enormous eruption when the North American plate attempted to tear itself into two separate continents and very nearly succeeded. It's the largest failed rift we've ever found. Every rift larger than this succeeded in creating an ocean. This one just barely failed. Hundreds of thousands of miles of lava were erupted, cubic miles. I mean, just enormous volumes. And at the tail end of that eruption, enormous rhyolite volcanic eruptions. Because as a magma body exhausts itself, the composition of the lava changes, and you end up with a higher silica lava. So at the tail end, you had these massive rhyolite flows oozing out and creating enormous mountains. I mean, these mountains were probably 15,000, 18,000 feet high. I don't actually know the numbers. I'm not sure anybody does. But they were absolutely enormous. And we know they were enormous because where they wasted away, they created thousands of vertical feet of Copper Harbor conglomerate. That's what I'm walking on here. And there are thousands of vertical feet of Copper Harbor conglomerate that were deposited. And all of this is made out of rhyolite clasts with the occasional basalt. For example, right here, you can see that's definitely a vesicular basalt that's mixed in with all these rhyolite clasts. But this is all eroding volcanic mountain. I don't know if I said that properly, but this is all eroding volcanic mountain that is preserved in these Copper Harbor conglomerates. And so when you find rhyolite pebbles on the beach over here, they've really been through a lot, because the rhyolites were erupted just over 1 billion years ago. And then not very long after that, within a couple million years, they were eroded away and washed downstream as big pebbles and cobbles and deposited in the Copper Harbor conglomerate, buried deeply. And then about 1 billion years later, they were exposed at the surface by the ice sheets that scraped away all the overburden. And those cobbles weathered back out because the cobbles are more resistant than the matrix material that holds them in place. And so when it undergoes weathering, those same cobbles that washed downstream 1 billion years ago and then got locked into this deposit fall back out of this deposit and onto the shoreline. So if you want to think about it in a certain way, when you pick up the rhyolite pebbles along the beaches here, those pebbles formed 1 billion years ago. Not just the rock itself, but the actual pebble itself formed about 1 billion years ago. and then was basically frozen in place, locked into the Copper Harbor conglomerate for 1 billion years, and unlocked just a few hundred or maybe a few thousand years before you found it yourself. I don't know how you feel about facts like that, but when I think about stuff like that, it's just amazing. It's an amazing world we live in. Wait, what's this? A 4th location in one video? Have I lost my mind? Well, yes, this is a 4th location. It is still on the Keweenaw Peninsula. Here we've moved to the south side of the Keweenaw Peninsula to a spot called Bear Bluff. It is just outside of Bettigree. Until recently, I used to love hiking here, and I was really looking forward to bringing you with me and showing you on the ground some of the rhyolites here. However, access to this location has been lost. Bear Bluff lies within the Miriam and Russell Grinnell Memorial Preserve, and Montreal Falls beyond it is in a private preserve as well. Both preserves privately owned, but publicly accessible. They're preserved for access to the public. They've got trail systems. However, wealthy landowners who own the surrounding land have put gates on the road and locked those gates, stopping people from accessing those public locations that we should have a right to visit. Listen, I get it. I live on a one-way street. There's a dead end. I don't like my neighbors all that much at the end. I don't like how many visitors they get. The guy runs a business and there's a lot of traffic and it tears up our road. I'm not thrilled about it. But I don't put a gate up on the road and stop him from being able to get to where he needs to go. The county, though, has been remarkably cool with these millionaire landowners cutting off access to the public to these public lands. Every year, it seems like the location of the gates change. Some are removed, some new ones are put up. The Keweenaw County Commission pretends that there is a back access to Montreal Falls, which there is not. I have never heard of anybody being able to get to Montreal Falls since the gate was closed. This preserve, you're allowed to walk past the gate, but you can't drive it. So you have to walk 4 or 5 miles just to begin the trail. And I didn't have time or energy to be doing that. Montreal Falls, there is no longer access, and it's very frustrating. These are public spots that millionaires should not be able to decide whether or not we can access them. The roads, I understand, cross their properties. They bought the properties that the roads go across, but they're public roads, they're public properties. At the end of those roads, the roads were already there when they bought the property, so people could already cross it. They knew what they were buying. The public has a right to access them. Okay, I'm done with my soapbox. Bear Bluff is a large section of exposed rhyolite cliff in a preserved rhyolite mountain, basically a preserved volcano that still has sort of its original shape that was later buried by other sediments and more recently exposed. There are several places around the Keweenaw where you can find these large rhyolite mounds, Mount Houghton, Mount Bohemia. These are both pretty nearby, and Bear Bluff here. But Bear Bluff is the best place to see exposed cliff face and exposed rhyolite rocks. Today, these mountains stand hundreds of feet high, but they're just a tiny fragment, a shell of what they originally would have been 1 billion years ago. They were thousands of feet tall at one time. It's remarkable that 1 billion years later, you can still find them standing hundreds of feet tall, thanks to the way they were buried and then re-exposed more recently. And on that note, I'm going to very annoyingly tell you to stay tuned for part 2. In the next segment, we're going to take a much closer look at the rhyolites you find on the shore and all the various textures and variations you find in them. So please join us next time as we learn more about these awesome rhyolites.